Let's look at what would cause a vertical stretch or a shrink or a reflection and what that means. If we look at the parabola x squared and we plug in, say, the numbers from -2 to 2, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 and 4. This gives us the points 0, 0, 1, 1, and -1, 1, 2, 1, 2, 3, 4, and -2, 4. So we get the parabola coming down through here. Something like that. Now, if I were to plug the same exact numbers in, -2, -1, 0, 1, 2, -2 squared is still 4, but if I multiply it by 2, that becomes 8. -1 squared, this is all going to be these x squared values doubled. So the 1 is going to give me a 2. 2 squared is 0 times 2 is still 0. 1 squared is 1 times 2 is 2. And 2 squared is 4 times 2 is 8. So now I've got the points. I've still got 0, 0 for the vertex. But now instead of 1, 1, I now have 1, 2. And -1, 2. Instead of the point 2, 4, I now have the point 2, 8, 4, 5, 6, 7, 8 up here. And the 2 is going to be, -2 is going to be up here. And so the graph every point is twice as high as the point on the black graph. So instead of 1, it's up to here. Instead of here, it's twice that far up to here. This is called a vertical stretch, and it is caused by, after you do the basic function to the x, multiplying it by anything larger than 1. The graph of c times f of x is the graph of f of x stretched away from the x-axis. So it's like you're stretching a rubber band, stretching it away. By a factor of c. On the third graph, where I'm talking about f of x is 1/2 x squared, it's going to be all of these x squareds cut in half. So let's try a different color. -2, -1, 0, 1, 2. I square it first, that makes it 4. Half of that is 2. -1 squared is 1, half of that is 1/2. Well, half of nothing is still nothing. Plugging in the 1 also gives me a 1/2, and the 2 also gives me a 2. So I've still got 0, 0 here. But now my 1 and my -1 each give me 1/2. And my 2 and my -2 each give me a 2. So now I've got a little short fat graph. So I should have specified here let me tack this on, provided C is greater than 1. If you multiply it by a number greater than 1, it stretches it. If you multiply it by a number between 0 and 1, it shrinks it back toward the graph, or sometimes they'll say condenses. There's other things they say, but in any case, it's going to push it back down toward the graph, so that if this is your graph, if this is your normal graph, multiplying it by something larger than 1 will stretch it, multiplying it by something smaller than 1 will flatten it out. Now, the other thing we need to talk about in this case is what happens when you multiply by a negative. For instance, say -1 here. If I take these same x values and I square them and then make it negative, this is the same thing as negative of x squared, exponents before subtraction. So instead of all positives, with the exception of 0, this is going to give me all negative numbers. And what happens is that now all of my y values are negative. And I have exactly the same shape as the original x squared, but flipped down. So if C is less than 0, which is math for C as a negative number, the graph is reflected. This is a vertical, all of this is vertical, so it's reflected over the x-axis. What would cause a horizontal stretch, shrink, or reflection? The vertical changes are always caused by changing, adding, subtracting, multiplying, dividing, whatever, after you do the main graph, the main function. So in this case, the main function is the square root of x. Notice the domain has to be from 0 to infinity because I can't plug in a negative. So I can plug in 0 and get 0. I can plug in 1 and get 1. I have to plug in 4 to get 2. I have to plug in 9 to get 3. You can kind of decide what you want your y value to be and then reverse engineer what you need your x value to be there. So I've got 0, 0, and 1, 1, but now it's 4, 2, 5, 6, 7, 8, 9, 3. This gives me the top half of a sideways parabola. What if we had the square root of 4x? The square root of 4x means multiply my x by 4 before I take the square root. So 0 is still going to be 0, but if I plug in a 1, 4 times 1 is 4, the square root of 4 is 2. If I plug in a 4, this is going to be the square root of 4 times 4 is 16, is 4. If I plug in a 9, 9 times 4 is 36, square root of 36 is 6. So what have I got here? It's 0, 0, 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 6. 1, 2, 3, 4, 5, 6. Multiplying on the inside before you do the main function pulls it up, but it's because it's pulling it toward the y-axis. The problem with this one is that this would be exactly the same thing as f of x equals 2 times the square root of x. So every point would be twice as high, but it would also be only 1/4 as far away from the y-axis. So where this corresponds to this, now it's only here. This point, well, I don't have another point. This would only be 1/4 as far away from that. These are much harder to picture, and most of the time, more often than not, a number that's multiplied times the x before you do a function can also be brought out and rewritten as the same function, but as a vertical stretch or shrink instead of a horizontal. What you need to know is that horizontal changes are always backwards from what you would expect, and they pull it toward or away from the y-axis. Let's see what it would do with the 1/4 x. If I plugged in these same numbers, 1/4 of 0 is 0, square root of 0. 1/4 of 1 is 1/4, and the square root is 1/2. 1/4 of 4 is 1, square root is 1. 1/4 of 9 would be 9/4, the square root would be 3/2. So this would result in 0, 0, 1, 1/2, 4, 1, 9, 1.5. And so it's pulling it toward the, well, this is pushing it away from the y-axis. This is stretched. They consider this stretched away from y. Or if you considered this to be f of x equals 1/2 times the square root of x, then it would be shrunk toward the x-axis. Now, f of x equals negative x actually reacts much differently from the negative square root of x. The positive square root of x was the green one up here. So here is our positive square root of x. The square root of a negative x, y equals the negative square root of x. Let me change that. Y equals the negative square root of x would be down here, reflected across the x-axis. However, in this case, because I'm changing the sign on the x, if I put negative x has to be greater than or equal to 0 to find the domain. When I divide by a -1, I have to turn this sign around. So that becomes a positive x, but a less than or equal to 0. Therefore, the domain of this is that x has to be negative. So the negative of a negative is going to go back to positive. So except for 0, I can only plug negative numbers in here. Negative 0 is 0, the square root is 0. Negative 1 is positive 1, square root is 1, and so on. That'll change these back. So the square root of negative x actually graphs like this. So let me review that. If this is y equals the square root of x, then this is y equals the negative of the square root of x. And this would be y equals the square root of negative x. And if you want to get wild and get all of them, this would be y equals the negative of the square root of negative x. So a negative multiplied times the x before the main function creates a horizontal change from there to there. Multiplying it after the main function reflects it over the x-axis, a vertical. This creates a vertical reflection. This creates a horizontal reflection so that it moves like it's along the horizon this way. Most of the time, we kind of try to avoid the horizontal stretch and shrink because you can usually rewrite it as a vertical stretch or shrink. We have something with multiple changes, and I'm going to assume you've already seen the left, right, up, down translations. So basically, c times f of x is, how can I write this with the fewest rules, is a vertical stretch if c is greater than 1 and shrink if c is between 0 and 1. F of cx, where we're multiplying the x before we do the main function, that will be a horizontal. What order would I want to put these in? It's a shrink if c is greater than 1, and a stretch for c between 0 and 1. That takes care of all the multiplication. F of x plus a is that's inside, so horizontal translation to the left if C is greater than 0, and right if C is less than 0. So if C is positive, it moves it to the left, backwards, and if C is negative, it moves it to the right. F of x plus A is a vertical translation. Going up if C is positive, and down if C is negative. Oh, and the reflections. Negative f of x is a reflection. Let me put in my vertical and horizontal here. This would be a vertical. Anything outside the parentheses is a vertical. This is a vertical reflection. F of negative x is a horizontal reflection. And these can all be combined. If they asked us to graph f of x equals x minus 3 squared plus 2, every point on this graph is going to be moved 3 units inside is horizontal and backwards. So it's 3 units right. And 2 up. So the graph that normally would have been here ends up going 1, 2, 3, 1, 2 to here. And there it is. If they ask us to graph f of x equals 3 times the absolute value of x minus 2, this is moved 2 units where? The basic function here is y equals the absolute value of x. So the 2 is on the inside, it's going to be backwards and horizontal. So it's 2 units to the right. And the 3 is on the outside. So it's stretched vertically away from the x-axis. By a factor of 3. So the absolute value graph normally looks like this. Like a V. And these would be at 45-degree angles. It's going to move 2 units to the right. 1, 2. So that's going to move it over here. But it's going to be stretched upward by a factor of 3. So this point that's currently this far away from the axis will be now this 1, 2, 3. And all of them will do that. So it's going to look like this. This one. Two units to the right and stretched. If we graph y equals the lines can be annoying because it's hard to tell whether something's on the inside or the outside. But you already know how to graph a line. The basic line bisects the first and third quadrant. That's y equals x. They call that the identity function. Because every point has the same number for its x and a y. If we multiply this by 3, it's going to pull it away from the x-axis by a factor of 3, or you consider it being pulled toward the y-axis. So it would either be 3 times as far away going this way, or only a third as far going this way. So if you take, say, this point right here, which is this far, it's going to be 1, 2, 3. It would be up here. But you could also consider that being only 1/3 of the distance from there. So this would be the line which actually has a slope of 3, right? The +2 is going to lift it up 2 units. So 1, 2. Let me change colors for the final version. So now it's going to run parallel to that. So lo and behold, what we have here is a graph whose slope is 3 and the y-intercept is 2.02. So when you get a line, you can still graph it using what you know about the slope and the y-intercept, and I would suggest you do that. Okay, so we'll call it quits there. Enjoy, and let me know if you have any trouble with it.